What's the most used man-made material on Earth? I'll give you the answer. Concrete. This is the Concrete Logic Podcast. Have you ever stopped to think about the sidewalks, driveways, bridges, or the buildings around you? They're all made from concrete. So why don't we discuss it more? In each episode of Concrete Logic, we'll explore a unique concrete-related topic with the help of industry professionals shaping the trade's future. We'll talk with suppliers, contractors, architects, engineers, specialists, and even proponents of competing materials. We'll get their views on concrete and their visions for its future. So get ready to mix things up with Concrete Logic, where we turn the spotlight on the material that's everywhere but often overlooked. This is the Concrete Logic Podcast. And now, here's your host, Seth Tandit.
Welcome to another episode of the Concrete Logic Podcast. And today I have Bob Higgins, Concrete Bob, back on the show. I always enjoy having Bob on the show. Learn a lot from him, and you will too. We're going to talk about rethinking moisture testing today. But before I get started, just to remind you, you can support the podcast in three ways. One is after you listen to this podcast and you learn something from it, I want you to share the podcast with someone, coworker, colleague, and don't be selfish with what you learned today. The second thing is go to concretelogicpodcast.com. There are two ways that you can get a hold of me. There's a contact link on the top of the page. You click on that contact link, and that's like shooting me an email. Or you can click on the microphone that's in the bottom right-hand corner of the homepage, and that's like leaving me a voicemail. And I'm looking for two things. I'm looking for topic suggestions or guest suggestions because I want to put out the podcast episodes that you want to hear and who you want to hear from. So that's important. And then the last thing you can do is, if you feel like you got some value out of this, if you learned something from Bob today, and you believe it has a monetary value to it, then feel free to click the donate button that's on the Concrete Logic Podcast homepage, and you can give any amount, and any amount is appreciated. With that, Bob, that's the quickest intro I've done yet. I only have you for 30 minutes, so I want to make sure we get all we can out of you today. So, Bob, we were talking quite a bit before I hit record. We want to talk about rethinking moisture testing in concrete. Where do you want to start?
I'm really glad you asked that, because I'm going to be teaching a building sciences class up in Jacksonville, Florida on November 12th. And I'm going to be covering some basics, because we keep going round and round with the different people about how to moisture test and what's wrong, what's right with it. And what really bothers me is everybody involved selling something that's a moisture test is always finding fault with somebody else's moisture test. They're all pretty accurate. The problem we're having is people do not know how to interpret the data properly. And so what I'm going to do, rather than jump into the heavy science of this, what I'm going to do is give a couple of examples that we were talking about earlier. I taught a class last year up in San Leandro to a union group of installers. And as I was finishing up, they asked me a question. They said, why is it that older concrete is drier, but we appear to have more problems with older concrete than we do newer concrete? And I started to explain that older concrete tends to collect salts underneath the finish or the coating or whatever else is on the concrete, and it will store that up. But what happens is it's somewhat inert because there's really no moisture source. Because I said there's this mistaken belief that moisture moves from the cooler underside to the warmer top side of the concrete. It doesn't work that way. But through diffusion, the salts will work their way up, because the salts tend to become more active with warmer temperatures. So there's this gradual movement of salts towards the surface. Then once you open up the concrete, now these salts have a new moisture source, the air. So they'll start gulping moisture from the air. And, they were kind of surprised by that. And they said, well, that makes sense. But they were reluctant to adopt it because it went completely contrary to what they've been taught. I said, I know it's contrary, but basically you're going to find out as you start jumping into this. We'll work back and forth, and I'll kind of help you through some of these moisture tests and the interpretation over time. And so what happened then is this moisture meter company went in 3 months later to show them how to use their moisture meters. And it was on a 42-year-old warehouse concrete. So they tested the moisture meter, it was 1.9%. They ground off the curing compound, they tested it again, it was 1.9% moisture. Well, they left and it came back somewhere. They weren't exactly certain what the time element was, but they said it was only between 10 and 15 minutes. They came back, and when they put the meter back down, it jumped to 4.3%. Well, everybody was shocked. So they got me on the phone. I said, well, I'm surprised it picked up moisture that quickly, but that's an object lesson. I said, one of the things that people don't understand is when you're dealing with a mineral-based product, and concrete is full of minerals, and it's full of water-loving materials that will attract water. It will hit dew point well before atmospheric dew point. Everybody's so focused on dew point. But what we have elements in the concrete that have dew point issues where it's much lower than the 100%. And I often use the calibration solution of sodium chloride, which is the same thing as table salt. If you put sodium chloride out in the air, and as long as the relative humidity is less than 75%, it stays dry. But as soon as the humidity rises much above 75%, it liquefies, it condenses. Well, that's its dew point. That's called ionic dew point. That is present in all concrete. So that's why I tell people, I said, we need that buffer of a 10 degrees Fahrenheit difference between the concrete and dew point. If you don't have at least that amount of a buffer, you're going to have concrete that's actively absorbing moisture. So when you go to test it, it's picking up moisture from the air, and people mistakenly, like they would have with that warehouse, if they hadn't tested right away, and then shortly after they would have, and they tested the next day like is normal for standard practice, they would have thought, well, look at all the moisture in the concrete. That was not moisture in the concrete; it came from the air. So it is time of installation testing that is so critical here. And as I've worked with the different installers where they've started doing time of installation testing, they've almost completely gotten rid of any of their moisture claims because they're catching these issues as they come up. Because if somebody, for example, very, very seldom will you ever find concrete that's as warm as the air. It's almost always colder. Water moves from warm to cool. I keep telling people that. So pay attention to that. So a summer day and somebody opens up the door and warm air blows in, you're going to get a burst of air that contains a lot of water because the warmer the air, the more moisture it holds. And all of a sudden it finds this cool concrete and it settles in and soaks in. So you can actually have a moisture issue introduced at time of installation. And this happens a lot.
Yeah. It's like a glass of ice water, right? The water beads on the outside. The water's not going through the glass.
Exactly. And it's not going through the concrete either.
Yeah.
Because one of the things that we found, and now it's been confirmed over and over again, is standard concrete, as we know it, cannot be cured properly to where you get a surface that's as dense and as has the same compressive value as the remainder of the concrete. So it is the top inch of the concrete that's really the issue. That came up again. Well, I like that illustration I sent you where they were doing basically this RH probe test, and it was in a laboratory setting, and it bothers me that concrete consultants saw that and didn't give it any regard at all. But in that study, it showed that the relative humidity towards the top inch of the concrete was reduced to 74%. Once the relative humidity of concrete drops below 80%, cement formation stops. So, and the longer that goes, the less recoverable that is. So you have permanently damaged concrete surface that's now more permeable and absorbs a lot more water and is weaker.
Mm-hmm.
So that's what's picking up the moisture from the air. But but everybody regards the concrete as being this monolithic, uniform sponge, and that's not the way it is at all.
Yeah, and this goes for new concrete too. I mean, your examples are old concrete in existing facilities that they're redoing, but the same goes for like a new floor, right? New concrete floor.
Yeah, and it's probably worse than it was back then, because since 2002 to 2018, the EPA required all the cement producers to reincorporate some of the flue gases back into the cement process. It's called cement kiln dust, and that's more alkaline. So they've introduced more alkalinity than we had in the past. Now it's to the point where the ACI and the ASCC, the American Society of Concrete Contractors, have basically informed engineers and specifiers that crilling and cracking is to be expected. It's not unusual, and they can go according to all the standard practices, and this is still going to happen. That didn't happen in 1950s concrete. You didn't get that kind of crilling and cracking.
Yeah.
Now we're being retaught and reconditioned to regard that as being normal. And so I like what the Texas Transportation Institute did, where they took the concrete, they water cured the concrete, they did one air cure and then one water cure. Well, the water cure was 7-day water cure. But what they did different is they sliced off the top 1 inch. So even with a 7-day water cure, the top inch of the concrete was a full 20% lower in compressive value than the remainder of the concrete. So even under a close laboratory condition, that the surface is still weaker. Now that collaborates and corroborates the relative humidity study that we saw before, where it showed 74% relative humidity in the top surface of the concrete. And that also correlates with the studies we're seeing now, where they're finally putting in these embedded humidity detectors and thermocouples, showing that when concrete heats up, within the first 2 to 3 weeks, the relative humidity in the top surface of the concrete can drop between 50 and 60%. Well, cement will not form. It does not form, no matter how much water's around it, because what happens is the warmer air and the alkalinity of the concrete prevents further cement formation. It retards cement formation, and that has a permanent effect on the concrete. And this is getting worse. So no matter how much you cover the concrete with this water, it's going to still be inadequate. We have to address that and realize this as a fact, not a possibility, but a fact. So if we start addressing that and start dealing with that time of installation, you can compensate for that moisture pickup by helping to dry the concrete out by driving wind across it. I have people setting up fans where I'll give a really good example. It's a 3-story building. And this was, I was doing some consulting work for this adhesives manufacturer. And they called me on the phone. They were panicked because they were going to delay the project because the 3 floors had a moisture issue. But interestingly, the 3rd floor had the highest moisture level, 2nd floor the next highest, and the ground floor had the lowest. They said, why did that happen? I said, well, that's the stack effect. The inspector on the job site didn't know what the stack effect was. The people don't understand building science. I said, what you're seeing there is warm air rises. It has more moisture in it, so it's going to be top down. It's going to be higher here, slightly lower, and then lower still. I said, well, how do we deal with this? I said, well, just put a fan on it. I said, take a concrete meter, put it on there, tell me what you're reading. So they told me what they were reading. I said, okay, as soon as it drops below 5%, you can go ahead and proceed. I said, what about the moisture still in there? I said, well, we need to get it to a point where it's low enough where it allows the adhesive that you're using, because it's not a water-based adhesive. Now, if it was a water-based adhesive, I'd tell you to get a lower number, but it's not a water-based adhesive. It will set and cure in time to where the moisture, as it comes back up and then basically re-equalizes, won't do anything to the adhesive. I said, are you positive? He said, yeah, I'm positive. Well, the inspector told me they needed moisture mitigation, which would have added 3 to 4 months delay to the project and added almost $1 million in correction. Well, they followed my directive where they blew the fans across the concrete. Once it dropped below 5%, they kept air movement, but they kept the fans advancing in front of the installers, so the installers were following the fans. It went down without a hitch, and it's been down there now for 9 years and hasn't failed. So they saved 3 to 4 months and almost $1 million of not using the moisture mitigation, because what was being moisture tested, was being misinterpreted by the inspector. This happens all the time. I cannot tell you. I've saved at least $10 million in avoided moisture mitigation that didn't need to be done, but if they had been done, they've been claiming, oh, look at this big success we have. Well, you're not interpreting the data correctly.
Yeah.
We need to start this time of installation monitoring, and once we do, I'll tell you what, I believe that this $3 billion a year problem we have now will be reduced to just a nuisance value. I don't think it'll even be in the millions.
Now the new concrete that has a weaker top, no matter what, right? I heard you right.
Yeah.
So what are we doing to compensate for that? Because I don't think you want to glue down floor covering on top of concrete that's got a problem in the top inch, right?
Well, that's where we kind of luck out, because again, of the second law of thermodynamics, because moisture wants to move from warm to cool. Well, as long as the surface stays warmer, it's probably not going to happen. It's going to go into kind of a stasis where it goes into its own type of equilibrium, because they've shown in concrete, you can have an area where it's 70% relative humidity right next to an area that's 90%. And it just establishes an equilibrium. So what that does, it also keeps the moisture and the alkalinity from building to a certain point. The only time I've seen that as a problem has been sometimes with epoxies, where they just assume these things are bulletproof, but you'll have a water miscible alcohol or phenol in your epoxy, and if there's alkalinity towards the surface, it'll pick some of that up and disrupts the curing process. Then later on, you get these little osmotic blisters. Now, there's epoxy formulations that don't get that. They're expensive, though. So, but I tell people, rather than go to that expense, just simply control your environment. If you control your environment to the point where you can put the epoxy down without it interrupting the curing and setting process, you shouldn't get any in these osmotic blisters.
Yeah,
that's caused by salt water, because it happens on boats. You put resin on boats, you see these osmotic blisters. It even happens on surfboards, where they put these epoxy coatings on surfboards, and if it's a salty environment, it'll get osmotic blisters.
Huh. So in the flooring covering world, there's not any kind of a process or standard that says you got to check your environment, your humidity, relative humidity of the ambient air and the temperature. Is that not a current process for putting floor covering down?
Well, thankfully this just changed. The National Floor Covering Association, I'll give them all kinds of kudos, just came out with a very detailed best practices that covers all that. It covers the testing, how to evaluate it, what's needed for the environmental control. It's very detailed, and I think, and they're offering it at free charge. So I would go to them, look them up. They're based out of Canada, And I think that's going to be a boon to all the installers.
Does the floor covering folks that's not polished concrete, they don't fall under that umbrella, do they?
No.
Okay. It'd be different process.
Yeah, polished concrete's his own set of rules there.
Yeah. Because I imagine they're having the same problems.
I don't know, because I'm not in that environment, so I don't know. I can't really speculate on that.
Okay.
You know, they're having that problem. How much of a problem they're having? We'll
skip that question. We'll keep us both out of trouble then. So these salts, I think we talked about in a podcast before. Where are these salts originating that are coming to the surface?
They're originating from the concrete. And now, one of the things I kind of geeked out last week, but they just found out that that salt water in the ocean behaves differently than they thought. So now they're realizing that all these climate models they did are incorrect because salt water doesn't behave in the same manner they thought it did. It actually creates its own little gradients. And I've been hammering on that. And even though the Portland Cement Association has recognized there's gradients in the concrete, that is not being adopted. It's being completely ignored. It's these gradients we have to deal with. At the top gradient of the concrete, if we take care of that, we're not going to have these problems. Now, later problems can occur if the concrete has some issues where it's got excessive alkalinity and under a pipe break or something else where water can be forced up, it can cause a problem. But under 99% of the conditions I can think of, that's not going to be an issue down the line, as long as we condition this at time of installation.
Yeah. We have
to be careful, though, because these are regional. In the desert, 4% moisture content with a moisture meter is too high. You want to be below 3%. So it's regional as well. People have to pay attention to that. There is no common figure that you can use across the United States. And that's the same with wood species. If you follow what the equilibrium moisture content of the wood species are through different parts of the country, that's really a good guideline for what we should do with concrete.
Is that going to be in that flooring best practice? I mean,
no, that was a little too esoteric, but I will cover that in the building sciences.
So you're saying if I'm in Washington State, that it'd be a different standard? What we're talking about, relative humidity balance. Is
Correct.
that a correct statement?
Correct.
In Washington State would be different than in Virginia.
Yeah, and Florida will be different than even South Carolina, because they have a wider thermometer than we do.
Huh.
But if you get it balanced in the equilibrium of when it's installed, those changes don't make a whole heck of a lot of difference.
Mm-hmm.
Now, where this does affect it, and I feel sorry for people that live in the desert areas like Arizona and New Mexico, their temperature underneath the concrete can get warmer than the room, and they can have all kinds of screwy problems that are caused by the concrete that even the epoxies can't withstand.
Like what?
Well, I wish I had the knowledge back then than I do now, but there was this epoxy failure, and we were trying to figure out, why it was so severe. Where they took up the epoxy, as soon as you put the pH paper down, it turned black, and the pH was 14. And then when we had it analyzed, we took a small sample of the concrete. The concentration of the sodium hydroxide was around 60%. I thought, wow. But we didn't realize that tends to just isolate at the surface. It doesn't go through. What it tends to do is tends to isolate towards the surface. Now, here's one of the other things why the building sciences and why we need to understand these things more. When you're in an environment like that, if that sodium hydroxide concentrates to 60%, the freeze point of that water sodium hydroxide solution is 125 degrees. So So it's acting like it's frozen water. You can't extract that using standard methods. So they couldn't dry they couldn't dry the concrete, and they didn't know why. Because we didn't understand the chemistry of what we were dealing with. Now, if I saw that today, I'd be able to fix it.
Yeah. When we're talking about building science and all this and moisture and humidity and all that, aren't we just trying to figure out how the water is balancing itself in the atmosphere? Like, you know what I mean? It seems like
it's always trying to seek balance, and that's why
right.
we get, it's always trying to seek balance. So you have to understand the environment you're in, and the environment in concrete is a whole lot different than the free environment of the atmosphere. So we have some different influences where you've got something that will attract water disproportionately.
Mm-hmm.
Now, that's where it's like some of these tests will have a value, but you have to understand what the value is. If you do something, say, like the calcium chloride test. Now, if the concrete's really alkaline, the calcium chloride test is not capable of drawing the water content out of the concrete properly. It will be inhibited because it's fighting another hygroscopic salt that's actually stronger than the calcium chloride. And that's why I teach in the building sciences class. The calcium chloride has a critical humidity threshold of 18%. So it's trying to dry the air down to 18%. But the calcium hydroxide in the concrete has a critical humidity threshold of 12.5%. So it's trying to dry it down to 12%. So the calcium chloride can't rob from this, but it can rob from here. It can keep it from being able to be picked up. The sodium hydroxide is even more dramatic at 8.5%. So you have to understand the chemistry of what you're dealing with. So when some of these, I gave a seminar over in Australia to the Restoration Institute, and I said, now, have you ever noticed that when you dry out the concrete, you get a rebound where it bounces back up? They said, yeah. I said, well, good. That's your drying point. I said, why is that drying point? Because just re-wetted again. I said, no, it's going into equilibrium because you over-dried it, but the alkalinity in the concrete is bringing it back down to its equilibrium point. As soon as it does that bounce back, now you're dry.
Mm-hmm.
They've started following that, and it's been really successful.
Even in Australia, where they're
just understanding the dynamics of what you're dealing with.
Yeah. Huh. I was going to make a joke about Australia, and I couldn't come up with one. Something about them being backwards or opposite of us.
Oh, yeah.
But anyways, yeah. Well, yeah. So I need to take your building science class, I think. So
well,
is it going to be, you going to dumb it down for a concrete contractor guy, or what is involved?
It's going to be really basic. I'm going to give tabletop demonstrations so things aren't so confusing.
Yeah. It seems logical that you should be checking the environment. If you follow ACI guidelines, they talk about how much, where's the wind coming from? What's the wind direction? Is it blowing across? We're supposed to put up windbreakers before we place concrete and check the relative humidity of the ambient air and things like that. That all impacts when you're putting down.
Because if you look at wind breaks, all you have to do is go to a construction site after rain. Wherever the wind's blowing, it dries the puddles out very quickly.
Yeah. Mm-hmm.
But if you go in an area where the wind speed is killed or eddied, it can sit there and stay wet for days on end.
Yeah. All right. Well, we'll end today right there. Bob, thanks for coming back on the show. I know you've been on here several times. I will share your contact information so people can reach out to you, maybe learn about those building science classes that you're teaching. So thank you, Bob. And
thank you, Seth, for having me on here.
Yes, sir. And folks, until next time, let's keep it concrete.
Thanks for joining us for another episode of the Concrete Logic Podcast. If you got value from the show, here's how you can provide value back to support the show. Visit concretelogicpodcast.com and click the donate button to send value back. All dollar amounts are truly appreciated. And now, to close out the show, here's Mike Dunton.
That alarm always sings couple hours before the sun comes up. Open up the side, put some diesel in the lights and wait till the trucks roll up. Yeah, this ain't how most folks live their lives, dripping in sweat, working overtime. But while they're tying their ties for their 9 to 5s, we're out here changing these skylines with wood, iron, and mud. We work hard for a dollar, give thanks to the Lord above. Never make a man do something you can't prove. Hard work calls for a drink or two. Expect more, it's written in our blood. With wood, iron, and mud. From the swamps to the city, from the Lone Star heat to the woods of the Georgia pine.